Hello everyone, welcome to the fifth lecture of Seismic. Today we are gonna be dealing with functions and calculus. It's the first of a series of modules based on the functions and calculus. Yeah, basically today it's the we are in the middle of the full module, so well done making it here. Okay, let me share my screen. As I was saying, today we will be dealing with functions and calculus. I've prepared some coding that I will share with you at the end of the lecture today. And let's start. So we will be dealing with the relationship between a mathematical function and a computational model of a biological process. The contents of today's lecture, as you can see there, we'll start by discussing the linear growth, and then we are moving to the exponential growth, and then we are going to see the continuous growth instead of time points, which is what we can see in the second, in that one here, in that part here. And finally, we'll be discussing the logistic growth. Starting with the linear growth straight away. Basically, as you are already aware, to create linear growth, we just add a certain amount of volume on every unit of time. On the previous volume, we are adding a certain amount of volume at every next unit of time. As you can see below in an example, we've got volume V equals with the initial volume and then plus the growth rate, which is constant, as we said. It's the specific amount. It can be, let's say, I don't know, 1 ml or whatever. And each time in each next step in every unit of time, every minute, for example, we are adding 1 ml. So if we start to, if the initial volume is 100, then it's gonna go 100 mLs, it's gonna go 101 mLs after 1 minute, and then 102 after 2 minutes, 110 after 10 minutes. That's the linear growth. Basically, it's that's a mathematical function. And it describes the process of linear growth, and it will tell us how volume of species evolves over time. It can be, for example, bacteria within a petri dish or whatever. How do they? Okay, this was not a great example because they don't grow in a linear growth, but we are gonna see them in a few minutes. So what we need to know here is those three parameters, and initial volume, the growth rate, and the time, and we can calculate the volume in each next time point. Here you can also see the units of each of the three parameters. And here's an example. Volume is, this is the example that you can see in your in the PDF with the notes, the seismic PDF. However, this is not a model. It's the solution of a model. And a more complex example will be, we will be seeing a more complex example in the next step, which where we can have both a mathematical model and a mathematical formulation. However, just to visualize something, I'm not going to explain the code here because we are going to see it later at the next examples. Basically, this is an unnamed function. Let me just run the coding for you to show, for you to see the to visualize, let's say, a linear growth model. Fplot, we are going to explain it later, is to plot a function, because we've got a function here, an unnamed function, and we use the fplot to plot it. Let me just, great. So that's how a linear growth looks like. It's constantly increasing, or it could have been constantly decreasing if we have been using a minus sign here. We are going to come back to discuss the plots at the end of this session. Moving to the exponential growth, we've got two types of exponential growth here, two examples of exponential growth. The first one is the one with the doubling time. So after a certain amount of time, in each unit of time, the population doubles. While on the second one, we'll see the exponential growth at each unit of time, where it doesn't double, but yeah, we are gonna see it later. We've got something different here. So starting with the doubling time, the exponential growth, we've got an example here where you, as you can see, n at time j can be any integer, and it defines the steps that we are gonna take. Let's say it can be one, step two, three, four, or we can see it in minutes, after 1 minute, or in hours, or in days, in years, or whatever. What happens after 1 hour, or what happens after 3 hours, or what happens after 10 hours. And to define this, we need the right hand side of the formula here, which basically says get the previous step and multiply it by 2. That's what we do here, and that's why we've got the doubling time in the exponential growth model. Let me first clear everything, and then let us define the model. We first need to note the time steps in intervals of time of doubling time, and what we are using here is 20 minutes for E. coli. Under certain conditions is 20 minutes, the doubling time for E. coli. So we set here the doubling time to be equal to 20 in minutes. Let me run the code as well. Yeah, we've got a variable named doubling time to distinguish it. And then we need 6 repeats. The reason I'm adding here 6 repeats is to have it for 2 hours. So we've got 6 times 20 minutes, which is 120 minutes or 2 hours. So we are gonna simulate this model for what's gonna happen if we wait for 2 hours. If we start observing the E. coli strain in for 2 hours. And a parenthesis here, this is now you'll start understanding the how useful MATLAB is. Instead of waiting for years or whatever, or months or whatever to simulate, to create an experiment and get the results, you just simulate it. You can simulate it, though it's not that straightforward. It's not that easy. It's not that accurate, not always, but yeah, in general terms, because there are a lot of variables that, or a lot of parameters that we need to take into consideration. And it's very difficult to get all the parameters into a system, most basically into a model, computational model, most basically because we cannot think of every single parameter. But yeah, let's proceed here, and we are gonna come back to this later. In order to create the time points that we are gonna model here start from 0, and they are ending at the doubling time times the repeats, which means 120 minutes. So we are gonna start from time 0, and we are gonna end 2 hours later. That's what we are basically saying here. And if I bring back what I had earlier, we are adding the steps here. So we are gonna go from 0 to 120 in minutes, and each step will be 20 minutes. So it's gonna look like 0, 20, 40, 60, 80, 100 until it reaches 120. Let's see how this looks like. As you can see here, 0, 20, up to 120. Each middle step, it's 20. It has a difference of 20. In order to get the number of time steps, I just created this variable name, number of time steps. We need the length of the time points. So it's the length of this variable here, which is basically all the values that it can take. If we run, so as you can see, we've got 1, 2, 3, 4, 5, 6, 7 values that are within the time points. We received the value, the length of this variable, and it's 7, indeed. In terms of the length, I'm not sure if we discussed it in a previous lecture, but yeah, I've added the link here for you to look at later on your own time. And then we need to initialize the population vector. It's basically a vector that will later on hold the variables, the values, not the variable, the values at each next step. So what the population will look like in step number 2, which is 20 minutes later. What will it look like 40 minutes later? What will it look like 60 minutes later? So what we basically do here is to create a variable named n for population, and we create a vector with all zeros with one row, and the number of columns will be the same as that one of the number of time steps. And it makes sense because we need to see what the population will look like at each time step. And we just, so if you look at n here now, it's 7 columns, 1 row, all equal to 0. In order to run the model, as you've seen here, the model will look like this. So we've got 2 multiplied by the population in the previous step. So if we start from step 1 and go to step 2, and we've got 2 multiplied by 0, it's gonna be 0, and then 2 multiplied by 0 in every next step, the answer is gonna be 0. That's why we need to create to note, let's say, the initial population. And here we are starting with 100. It could be anything. I just arbitrarily set it to 100. So when now will look like that, starting with 100. And when we do the simulation of the model, we'll see how this will look like, how these values will look like. To do the simulation, we'll use the for loop. function. We came across it in the previous, or in the two previous lectures, so you are familiar with it. We just initially set j, which is the number of steps, and we set it to start with 2 because the first one is already done. So the first one is going to be equal to 0. The initial population is going to be equal to 0. And we need to see the second, and then the third, fourth, fifth, sixth, seventh step. So we are going to start with step number 2. Here we are going to get the value, and then proceed to number 3. So in the second loop, that's going to happen. The j is going to be equal to 3. The fourth loop, the j is going to be equal to 4, and so on. Third loop, sorry. And it's going to end when it reaches the number of time steps, which is equal to 7, as we saw earlier. So at the first loop here, at each loop, basically, we need to get the new population number. Let's say in the second one, if j is 2 at the first loop. And what's going to happen is that we are going to multiply 2 by the previous population, which was 100. We've got a rate, a constant rate here, because we need to double the population at each next time step. And that's the difference with the next example. But let me come back to this in a second. So let me run this piece of code here, and let us visualize. And so, as said earlier, we start by 100. At the 20 minutes later, at the next step, this value doubles, goes to 200. One step later, 400, 800, and so on. In every next step, it doubles. And I've got some coding below to plot it, to visualize it, and see how does it look like. So when we plot, we just use the time points, which is the variable holding the 7 time points, 20, 40, 60, 80, etc. As you can see here, we need the population number as we've calculated it right now. And then we plot them together in the X and Y axis. What I'm doing here is to change the dots into stars and make them blue, just to distinguish them, and increase the marker size to 20, just to be easier to visualize. And then we've got 2 more functions. I've added them in the end, so you can look at them at the end of this lecture. They are pretty much the same. The one changes the label in the x-axis, the other changes the label in the y-axis. And I just give it the legend time in minutes, and I increase the font size. And then the other one is the population number at each step, each j step. Let me run this part of the code as well, and you can visualize it here. Let me make it a bit bigger for you to see. As you can see in the y-axis, we've got the population number going up to 7,000, but as you remember from what we can see here, 6,400 was the greatest value that we got, and you can see it here with a blue star. And then 100, which was the lowest at 0 minutes, that was the starting population. And in between are all the others. For each basically, yeah, in the x-axis, we've got the time in minutes. And at each next step, and we can see that every next step is 20 minutes, we can see the population number, which basically doubles exponentially. It increases exponentially, and it basically doubles. Moving on to the next example, it's pretty much the same. We are doing pretty much the same as what we did in the previous example, but instead of having a doubling population, we got a different rate of increase. And this rate is given by 1 plus R. This was given in the PDF. In equation 1.1.4. You can look at it later on. And basically, we've got the fractional growth R calculated from the doubling time. As you can see, R equals, or basic, yeah, R equals 2 into the power of 1 over doubling time. Minus 1, and then minus 1, or we can rephrase it, or change the place of minus 1, go to the other side. So we've got R plus 1 equals to 2 in the power of 1 over doubling time. And this is what we will be using as the growth rate in our when modeling this this function. As you can see here, we've got the step. Basically, what we add here is the number of steps. The time steps will be in intervals of 1. So we are gonna see it in every minute. The doubling time is still 20. The repeats are still 6. So it's the same as the previous example, but this time we are gonna visualize it in the steps of 1 instead of steps of 20, as what we had in the previous example. So again, this is the same as before. From 0 to the doubling time times the repeats. So from 0 to 120 minutes. But this time, the steps in between are not going to be 20. It's not going to be equal to doubling time. It's going to be equal to steps. So in every minute. On the right, I commented what's the difference with the previous example. Again, the number of time steps is the length of the time points, is the same as before. And the initial population, to initialize the vector and add the initial population, it's again the same. We are starting with 100 units of population. Let me just run this code so far. So we've got it. And then here's the new. We are trying to create the constant for the rate from R plus 1. And I named it R plus 1. And it's equal to 2 in the power of 1 over doubling time, as we saw in the example in the PDF. So I'm just adding this, I'm creating this variable as well. And then we are gonna simulate the model again with the same way, using a for loop. The steps are gonna start from 2 and finish when they reach the number of time of steps, which is 7. And in each step, the R plus 1 growth rate is gonna be multiplied, or basically the previous, to put it in nicer words, the previous population or the population at the previous step is going to be multiplied by the growth rate, which is the R+1 here. And so we are going to create the exponential growth. It's not doubling time this time. Let's see it, and let's visualize it as well, same way as before. As you can see here, we again have the time in x-axis. In y-axis, we've got the population. You can see the exponential growth. You can see it though in each step of 1 minute instead of 20. So you've got much more data points here. And if I zoom in, even though that it looks crowded here, you can see that they are distinguished in, let's do it here. So in, let's see those two, as you can see from the 15 minute, the next one is in the 16th minute. So we can see that they are distinguished. They are not in a single line. We are gonna see this in the next example though. Here, as you can see, I've got the links to the functions that you need to revise yourself. And as promised, in the next example, we are gonna see the continuous function, the continuous exponential function, which is basically the solution of the model. And you will see a line without different points to be distinguished. They will be all together in a line. It's not going to be a straight line because we've got an exponential. It's again an exponential function. We've got here the exponential function. It's basically constant k times the time, and it's the exponential of this value. We first need to calculate the growth rate k. We are gonna name it k for the exponential function. And in the session PDF, the equation 115 specified it as the ln, the natural logarithm of 1 plus r, or r+1, as we saw earlier in the previous example. So this example that we are seeing here now is using the same values and the same variables as those created in the previous example. So the natural logarithm in MATLAB is created by the function log. And yeah, I added it here so you can, yeah, natural logarithm. You can revise it on your free time. So to calculate the growth rate, we need to logarithm to get the natural logarithm of the r+1, which was calculated earlier. That's the r+1, and the natural logarithm of r+1, which is the growth rate k, is calculated here using this piece of code. Then we need to add the initial population. As we did earlier, we are going to use the same as that in the previous example with 100. And now we are going to see the solution. We create, as we did at the very first example with the linear growth, we use the anonymous function to run to model, to see this model. The way we create an anonymous function is, first of all, to add the sign to define the variable. and we use t for time, and then after leaving a space we add the equation that we need to run. And I mean when we are running this function. So the equation that we are gonna run is at every step, every next step, we get uh, the initial population or the previous population, and we multiply it by the exponential growth, by the exponential of the constant k times the time. And before plotting it, we need to specify the limits. What we do here is to have the limits from 0 to the number of time steps. The time steps are 121, including 0, because we are having a time step at each minute. So by running this piece of code, we've solved the model. We got the solution of the model, but we haven't plotted yet. I've deleted the previous plot, so let me run it again. So we'll have it. Okay, here is the previous plot that we saw earlier in the previous example. And let me now create the plot for the example that we are dealing now, the continuous one. And I'm gonna overlay it, add it on the top of the previous plot. To do that, we use the hold function, and by adding on every next plot that is created is gonna be added on the previous plot. It's not gonna create a new figure in each next plot. I added the link here so you can check it yourself later. So I first run the hold on, and then I run the f plot. As said earlier at the beginning, we use when we are plotting, when we are creating a plot from a function like the one we've got here, the anonymous function, we need to use the fplot function. And then it's the same as the plot. We specify the y and the x axis, and then the color, the line, the color of the data points, the line width, etc. And anything else that we need to specify. So I'm now plotting this, and it's gonna be overlaid on the previous plot. So if we look at the plot now, we can see the stars that were they are from the previous example, and it overlaid the magenta colored line, which is the one we created now using the continuous function. Let me zoom in a bit so you can see what's going on. So even though we've got a time point at every step here, at every minute, there is no separation of the time points, it's just a line. Here, I've got some scrutinizing the data, basically, to find find what what we might need to find uh, based on the task that we want to achieve. Basically, here what we are trying to do is to find the population which is larger than 1,000. So at which time point the population is going to exceed 1,000, and what we can do is to plot a line. Okay, here again I deleted the previous plot, so let me create them again. Okay, what I'm doing here is to plot a line at the 1,000 where population equals 1,000. What you can see here, if I make it bigger, so you can see that we plotted a line where the population is equal to 1,000. Whatever is above this line, it exceeds 1,000. And if we zoom in here where one crosses the other, it's we can go down and find the minute, the exact minute when the population is going to cross the population equals 2,000. However, to have in clear values here, what we can do is to check which values are larger than 1,000 using the population greater than the logical input greater than 1,000, and the find that we found we saw in the previous the find function we saw in previous lectures, and it's basically to find the indices where the values of n exceed the value of 1,000. And what we can see here is that from 68 into 121, all those values exceed the value of 1,000, as we saw in the plot here. And then if we need to see, or if I was using the smaller than, we will see all the values that are below 1,000. It will be from 0 to 67, basically. If we are looking to find for the time point when it first exceeds 1,000, then we need to get the values above 1,000 that we calculated here, all those values, and just get the first entry, which is 68. So if I run this piece of code, the answer is 68. So at the 68th time point, it first exceeds 1,000. The population first exceeds 1,000. And if we need to look at the population at that time point, in order, for example, to compare and see by how much does the population exceeds the 1,000, we need to run this part of code. So give me, what I'm basically telling MATLAB here is give me the population when t at the first point when the population exceeds 1,000. As I calculated it in just running this, and we can see that the population is 1,019 at the time step of at the 68th time step. Have a look at the links that I've added here, especially the anonymous function. It will help you make things clearer. It will help you understand things much better. And obviously, let us know if you have any questions, so we can respond straight away and help you with that. There isn't much time left, but I'm gonna proceed to the logistic growth evolution. I'm gonna run through it. Basically, what we are looking here, and as you will read in the PDF, please read the PDF. It will help you understand the biological reasoning behind what we are doing now, behind the modeling that we are doing today. What happens, for example, when we've got limited resources? So the logistic growth model assumes unlimited resources, but the growth rate decreases as the density increases. In a petri dish, for example, if the cells that we've got in a petri dish keep multiplying, the density increases, and therefore the growth rate decreases. When they reach 100% density, they will stop multiplying. They will stop multiplying themselves, unless they are cancerous cells. But yeah, let's not get into this this example now. The model is given as a differential equation. Basically, what I wrote here is to see the difference between the two. In the exponential growth, the rate of change was R0 multiplied by Y. In the logistic growth, the rate of change is the same, but we add another term here. And basically, we expand it, we expand the exponential growth, and basically the first term, one here, is just the logistic growth, and the second term is it depends on Y, and this is to make sure that if the population grows and gets large, there is something to bring it down again. That's why K is Y is divided by K. What we do before doing the logistic regression model, the logistic growth model, sorry, we need to define the symbolic variables, and it's the function sims. But if you don't have the symbolic math toolbox add-on installed on your MATLAB, this is not gonna work. So what you need to do is to download or install basically the symbolic math work add-on. You can do it from home add-ons, and then search for the symbolic math tool and install it. So what we do here is to define the symbolic variables, and basically what each symbol stands for here. Y as a function of t is the population as a function of time. N0 is the initial population, R0 is the growth constant, K is a scaling factor, and T is the time over the simulation time. To define the differential equation this time, basically the differential equation is the equation of the y of t function. And we define it using the diff function. I added the link below so you can look at it later on your own time. And what we do is to add this differential equation into a variable named diff EQU, and then differential stands for differential equation. And yeah, what I was saying here is that we use the diff function y of t, and then we use the logical equal, which is written as equal, as you can see here. And then we've got the exponential growth as we've got the logistic growth. As said earlier, those two are the exponential growth, and then it's expanded by adding this term here. And we've got the logistic equation. Let me just run this. To solve this equation, we using the initial population, the n0, we use then the solve function. I also added the link below and the simplify as well that we are gonna see in a second. So by using this function, we are trying to solve the equation. We are adding the solution into a variable named solution. And basically here within the brackets, not brackets, the inverted commas, we are specifying the started value for y0, which is equal to n0, the initial population. And then when we run this, we will need to simplify it because it will look, let me show you how it looks like. Here's the solution of the equation that we create, of the differential equation that we created earlier. Here's the solution, but it has logs in it, and this will create some trouble considering negative or positive values, etc. So we need to simplify it. That's why we use the simplify function, and in brackets we add the solution variable in the previous step, and it will now look like this, which basically it doesn't look to be simplified, but it actually is. It doesn't include any logs in it, and that makes our lives easier. Then before plotting, we are going to proceed to plotting the solution now, so you can understand what's going on. But before proceeding to plotting the solution, we first need to convert the symbolic to an algebraic function. And we achieve this by using the MATLAB function name. That's the name of the function. Again, I added the link below so you can look at it yourself on your own time. And what we do, okay, we create a new variable named solution algebraic, because that's what we are gonna do. And in this variable, we add the outcome of what we are gonna discuss right now. So MATLAB function of the solution. So we are saying get the solution, the simplified version of what we found from the dsolve above, get that solution and convert it into an algebraic function. So we can then use numeric values in order to be able to plot it. And we are then specifying the variables of that we are going to deal with, and we specified them in square brackets as a vector. Running this as well, and then we are going to use numeric values for the cost constants. I'm using two different initial conditions here for us to compare. Initially, I'm using the initial population, and 0 is the initial population as said. I'm using 1 for 100 units of the population, and the second one is 150 units of the population. And then for K, I keep the same 1,000 in both cases, R0 same in both cases, and T, we don't specify T in this step because we create an unnamed function for T. And yeah, here is the function, basically the solution algebraic, but we add the numeric values. The first one, because it starts from 100 and grows to 1,000, it's a logistic growth. The other, which starts from 1,500s and ends with 1,000, that's a reduction. That's called a logistic decay. But let me run the code here and plot it, and I'll show you what I meant. So because we are plotting two different equations here, I'm using again the hold on function in order to plot them both at the same figure. So I create a new figure. Sorry, I create a new figure. That's an empty one. I use the hold on. So every next thing that I am plotting on, every equation that I'm plotting on this is going to be plotted on the same figure. I add the limits within which we are going to plot this equation. So starting from 0 to 300 minutes, for example, or 300 years, or whatever. It depends on the units that we've added in the equation. So I'm adding the limits as well, and now I'm plotting the two. Let's start with the one. So you can see we've got one equation here, and now I'm adding the second equation at the same plot, the red one. One is blue, sorry, one is blue. The first one for 100. The second one starting with 1500s is red. And let me add the X and Y labels as well, so you can distinguish, you can see what we've got here. And I'm also adding a legend. I'm naming it logistic growth and logistic decay. Growth is the first one, decay is the second one. So I'm adding them at the correct order. In terms of the legend function, I added it at the bottom so you can visualize it yourself. So what we've got here, here is the legend, by the way, that we just added. And the two equations. The first one, the logistic growth, starts with 100 at time 0 in 0 minutes, and it grows exponentially up to 1,000, where it reaches a plateau phase. And okay, I stop here. I mean, I added the limits up to 300, but if I had a greater number, 3,000 or whatever, even a million or whatever, that would have been a constant, a straight line, because it has reached that plateau. The same happens for the red line, but the other way around. So it started higher, it goes down to 1,000. That's an exponential, that's a logistic decay, and it reaches a plateau phase at 1,000, and it keeps being, it's constant. It keeps being at 1,000. That's all for today. We've covered everything and on time, though we didn't had more time to explain in more details. Please read through the PDF. It's very uh, it will help you understand from the biological side as well what's going on, and why did we apply these functions and this kind of calculus. And if you've got more questions after reading the PDF, don't hesitate to reach to ask us directly your questions. Thanks for your time and see you soon. Bye bye.